Welcome to our STEM lecture series. I'm Brian Kurth from the Math Department, and I'm pleased to welcome you to our third and final STEM lecture for the semester. STEM, as you may know, stands for Science, Technology, Engineering, and Mathematics. And I'm very pleased to introduce to you our speaker, Dr. Gary Navrotski, who comes to us from the Advanced Photon Source at Argonne National Laboratory. Gary has a bachelor's in physics, a master's in materials engineering, and a doctorate in materials science from Cornell University. He has worked in many places and taught and done research in many places, including NASA on the space shuttle. And now he works in instrumentation and X-ray and optics design at Argonne. So Dr. Navrotski will speak for about 45 minutes or so. If you have questions during the lecture, we can take those. And then we'll have some time for Q&A at the end as well. So without further ado, I give you Dr. Navrotski.
Thanks, Brian. Thanks, everybody, for coming out through the rain and the wind and the leaves and the campaign posters to hear something about STEM. STEM is more than, some of you think it's 4 different disciplines: science, technology, engineering, math. For me, it's all one big interchangeable ball of knowledge. It's a way we've come up with for solving really, really difficult problems through logic, through communication, and through very complicated computation. I'm going to tell you about this place at Argonne National Lab called the Advanced Photon Source. First, let me give you the big picture here. So here we are. This is this airplane view. Here we are at beautiful Moraine Valley Library, up in the library. And if we just take a short trip over the river and through the woods, over here to Argonne National Laboratory. Oh, this does not work. That's great. There we go. Whoops. I work in this building. It's a big ring. You've probably seen Fermi National Lab, a big 6-kilometer underground ring. We have a 1.4-kilometer building, circumference building. And this building houses a similar kind of ultra-high vacuum tube where we send electrons down at the speed of light, and we do experiments with them. And I'll tell you all about that. So usually I talk to people, and I love describing what I do, but it's a little hard, it's a little complicated, and I usually meet them in a social situation, and then they obviously ask me, what do I do? And this is where it gets hard. What do I do for a living? Well, I try to be exact. I try to say I'm an engineer, I work at Argonne with high-intensity X-rays. And usually their eyes kind of glaze over, even though it's a very exact description of what I do. Their eyes glaze over, and I don't know what they're thinking. I think they're thinking I work like this. I'm an engineer working with X-rays. And that's not what I'm trying to say. And so I usually step it up a notch. I try to more exactly define what I'm doing. I say I create the most brilliant X-rays in the world, and here's how we do it. So I have to start with the basics. So you guys have been in a dental chair or a medical facility. You've had an X-ray. You sit in the chair. The technician puts this heavy lead cover on you, cover your thyroid. And then they leave the room. Okay, that tells you something. And you hear a little zap. And what that is 1,000 volts of electricity jumping across and hitting into a tungsten target and creating X-rays, which shoot through your head and make an image of your teeth. If you've had a CT scan, you've had something similar. You lay on this bed, and they circulate the X-rays around you and make a 3-dimensional image of what's going on in your body. Well, we do something that's almost but not quite entirely different than that. We have a building here, this Advanced Photon Source. It's about the same size, you can see, compared to Soldier Field and, sorry. No, it's not Comiskey. No, it's not US Cellular. There you go. It's bigger. It's compared to those three buildings, they can all fit inside of it. The Sears Tower, not the Sears Tower. The Willis Tower can lay down inside. And like I said, it's a big circular racetrack for electrons. And what we do is we put bunches of electrons and we zip them up to 7 billion electron volts energy. And we circulate them around at 99.999999% of the speed of light. If we would let these things go, they would go around the Earth 7.5 times in 1 second. They're really going fast. This is the first trick we use. We use relativity every day. If you would have told me as a kid that I worked in the relativity field and quantum mechanics every day, I wouldn't have believed you. I would have asked myself where my flying car is and where my ray gun is, but I wouldn't have believed that I use these things just every day. We apply relativity, and what happens when we send these around so fast, these bunches of electrons give off intense X-rays, super intense X-rays. And because it's relativistic, in our frame of reference, all the light comes out pointed forward, sort of like a headlamp on the front of a train. It all shoots off tangent to the track that these electrons are going around. How do we keep these guys going around in circles? Well, electrons have a charge of -1, and we put them through powerful magnets. And these magnets bend them around. How would you like to have one of these magnets in your sticking to your refrigerator? It's a super high field. And we bend the electrons around this ring, around this track. And so as we bend these electrons around the track, the electrons are coming here. This red thing is one of those magnets. The X-rays that come out, they come out straight tangentially off the ring, and we bring them into these lead-lined rooms where we do all kind of experiments. We use these X-rays to create 70-meter long, it's about the size of a football field, 70-meter long X-ray microscopes. And we have 68 of them in this one ring, 68 of these super powerful microscopes. And because these electrons are going around in bunches really fast, they're flashing super fast, flash every 15 nanoseconds. Sometimes you care. Sometimes people like to just have that strobe light effect. Sometimes they don't care. If these are fluorescent lights here, you don't care that that fluorescent light is flashing on and off 60 times a second because you can't perceive it. But there are things that can use the flashes, and there are some experiments that just use the intensity of the X-rays. So another trick we use is sometimes, instead of bending them gently and letting X-rays come off gently, we send them through a washboard of 33 magnets, super bright, super high intensity magnets that shake these electrons around and generate super high intensity coming out of that device. This thing is called an insertion device. So it's just a bunch of magnets that shake the electrons around and have them emit huge amounts of radiation. What do these beams look like? If you could look at it with the eye that you don't want, you would see it's about 200 microns high. What's that? So a millimeter, your thumbnail is about a half a millimeter thick. So if you feel your thumbnail is about this thick. So the beams are about a thumbnail wide and about a tenth of the thumbnail high. That's what they look like right now. And we're completely tearing out this place, and we're going to put all those X-rays into a tiny little spot. We're going to upgrade this source to make it even, make it 1,000 times more brilliant than it is now. And with all that X-rays comes a lot of heat. How much heat? Well, I'll give you some relative numbers. If you could take a square millimeter of the sun, there would be 60 watts coming out of a square millimeter of the sun. You know what 60 watts is. Well, maybe you all use LED light bulbs. 60-watt light bulb. Imagine putting your hand around the filament. That's 60 watts of power coming out in all directions from that. So from the surface of the sun, if you could take a square millimeter of the sun, you'd get about that amount of power coming out. Well, the power that we have to deal with is 430 watts per millimeter square. So that's a lot of power coming out of this X-ray machine. We almost have a megawatt of power that we use all the time. And it tends to burn through things. This is one of my early mistakes. I tried to focus the beam and stop it with a coin, and it didn't work so well. So happens all the time. So my job is to take these X-rays and shape them into the useful kind of beams that they can use for all different kinds of sciences. And all this X-ray power has to stop. I have to stop it somewhere. And that's a big part of the problem. I have to stop all this power somewhere. So I have a trick. I have a bunch of tricks. 3 more tricks that I can use. First, I use mirrors. Okay. Pretend that you were getting a chest X-ray. And they're going to take a chest X-ray. If you held up a mirror to yourself, what would happen? Nothing. X-rays just go right through it. But if I make this mirror atomically flat, I polish it till the surface roughness is less than an atom high, and I take the X-rays, I can skip them off the surface. So I can bend this thing slightly in different directions, I can skip it off the surface, and I can make these X-rays, I can focus them, I can move them around. It's hard to move around X-rays, they just go through everything, but I can move them around and focus them. That's part of the reason that these microscopes are 70 meters long. I can only move them by tiny little amounts here and there. And this is what one of these X-ray mirrors looks like. It's a large piece of silicon, polished atomically flat, and we skip the X-rays off the surface. And we can bend them slightly, and these X-rays will come in and focus to a much smaller spot. And this is what it looks like in animation. We take usually silicon, sometimes copper, highly polished, coat it with a coating, and we bend it just slightly and focus these X-rays. And so that's one of the tricks we can use to control X-rays. Yes, they go through everything, but we can do some tailoring. A second trick I can use is very similar to a prism. You guys know that you could take white light and put it through a prism and you get the color of the rainbow. Well, I can do something similar. The X-rays coming out of this machine are a full spectrum, like white light, and I can put them on a few crystals, and I can select out one energy or one color very exactly. And so I can take these crystals, single crystals of silicon. If you've seen a diamond, you know the diamond is a single crystal of carbon. This is a single crystal of the exact same atomic structure, but made out of silicon. And it will select out exactly one energy of X-rays. And this is what it looks like. This is my friend Waquette. This is a crystal of silicon. X-rays come in. This thing is cooled to liquid nitrogen temperatures, 77 Kelvin. That allows this thing to take a whole bunch of power and turn it into a single color of X-rays. So that's another trick I can use to play with X-rays. And the final trick, I really don't have many tricks. Final trick is I have to suck up all this power that's coming out of this machine. And I do that by spreading it across large blocks of copper. And this is just a geometric trick. It's kind of like we're on Earth, and the sun, the same sun on the equator, has a different amount of heat than the sun at the North Pole, because at the North Pole, the sunlight is spread out longitudinally across the thing, and it doesn't heat as much. I do the same thing. I have huge blocks of this special kind of copper. It's a copper that's made out of tiny crystals. Each of these little orange things are crystals of copper. They're smaller than the diameter of a hair, and they're all mashed together into this special composite material. And the way we do this is we actually put this copper in the ground and we blow it up. We physically bury it in the ground, blow it up, and form this material and clad it to copper. And it looks like this. This is normal copper, huge crystals, and this is the special kind of copper. And when you explode it, you see these wave patterns, just like the waves off a bow of a ship. It's a shock wave. And the two have bonded together. And I can use this special, very, very resistant copper to take all my X-rays, turn it into heat, and get rid of it. And it makes pretty patterns. There's a lot of detail, a lot of stuff going on here. Things are melting, things are bonding, things are atomically shifting all around. So my job is to build all the devices that take this super strobe light of X-rays, all this power, all this energy, and make it into the shape and size and color and configuration that they need for experiments. So I'm going to show you now some of the things we do with these kind of X-rays. An X-ray is exactly like a microscope. I mean, who can use a microscope? Just a professional? No. Everyone. Every hospital has a microscope. Every chemistry lab has a microscope. These are very, very versatile tools. First, to start with the basic, this is the very first X-ray ever taken in 1895. William Rankine, when he announced to the world that he's discovered X-rays, he sent this picture to the Royal Society in London of his wife's hand. And she had a ring on, and her bones, and you can't see her skins. And she was very distraught by this photo. She is quoted saying she has seen her death, and she was very upset. But this is the first time anyone's seen through people. And this is the very first X-ray ever taken. And even to this day, we have lots of fun with this. We have all kind of jokes. Sid and Harris had this nice joke. William Rankin's first attempt at X-rays, he was trying to shine a light through Madam Rankin. We just enjoy that this was the first announcement of the discovery of X-rays. And you guys have seen X-rays, chest X-rays, we do X-rays of wells. This stuff is called absorption contrast imaging. Things that are denser will stop the X-rays, and things that are less dense, like your bones, will stop the X-rays, and things that are less dense, like the air in your lungs, do not stop the X-rays. So it's just absorbing at different rates, and it's called absorption contrast imaging. We don't do much of this. Everyone does this. X-ray machines are all over the world. Every vet's office in the world has an X-ray machine that do this kind of imaging. We do things that are much, much more complicated, and I'll give you some examples. I'm going to start contracting the length scale that you're used to working with. And I'm going to start with this guy. This is a tomato hornworm caterpillar. He's about the size of your fingers. Biologists love using these X-rays. This thing turns into one of these beautiful, what's this moth called? It's called a hummingbird moth, yes. So if you see one of these guys, it's bad for your tomatoes, but good for an environment. Anyway, the biologist wanted to look at this guy in detail. They wanted to see how he walks. He's basically a bag of water and goo. You do an X-ray of him, you see nothing. You see nothing. But we can do a technique called phase contrast imaging, where we throw away all the X-rays that go through him and just look at the ones that are, we call it phase shifted. It's sort of like putting, what are those glasses? Like Polaroid glasses on. It throws away all the scattered radiation and lets you see fine detail. And so what these guys did is they put him on the stick, and we moved the stick, and we're trying to look at how his knee works. How is he getting around with no bones? He's got no bones. He's just a bag of fluids and air. And so we put him in the X-ray beam, and we watch him crawl. And this is the image. And you see all this detail in there. There are these long structures. These are air sacs that are bringing air in through these little spots and pumping it throughout his body. And you see stuff going this way and stuff going that way, and you can see the structure of his knee. Very, very fine detail. And they were able to figure out how this guy walks, and they came up with a mathematical model for how this is done after analyzing all this high-resolution imaging. And basically, he's pumping fluids between different chambers of his body, and there's a central core with some flap doors in there. And just by hydraulics, just pumping different fluids to different parts, you can make things move. And of course, the engineers saw this, and they loved this kind of stuff. They came up with a way to use this. If we're going to have future robots doing stuff for humans, do you want this big mechanical arm coming at you, maybe taking your temperature? Or do you want a nice soft robot coming at you and taking your temperature? You want to use something soft. And so they, with these pumping of different things, they've come up with ways to animate all kind of things. Soft robots. It's a whole new field. And we learned all this from this tomato hornworm moth. And of course, they have to animate some cool stuff. So we talked about something the size of your fingers. Now I'm going to shrink your length scale down to the size of a fruit fly. You've left bananas out too often, right? You've seen these little fruit flies hanging around there. So these little guys are the playground of biologists. They can mutate these things in 2 days. They can make any kind of genetic mutations of fruit flies that they want. They can make ones that are super bulked up, super flyers. They can make ones with tiny little vestigial wings. They can create all kinds of mutations. And my friend at IIT, Tom Irving, wants to look at the muscles in this fruit fly's back. How do muscles work? We don't know that. So they want to see in flight how muscles actually work. And so he takes these fruit flies And they're pretty easy to work with. If you touch their feet to a card, they do not fly, and if you take the card away, they do fly. They figure if their feet are touching something, they're flying, so they start flapping. And he shines X-rays through their back and looks at the muscles. The X-rays go through this hole. We don't care about that, but we look at the X-rays that are scattered very close around the direct beam. And these patterns, the small angle scattering patterns, tell us about the fibrous structure, the size, and how this whole muscle, myelin sheath, all this biology going on, how that actually works. And so he's spent 15 years of his life trying to figure out how muscles work. On a molecular level, how does a muscle work? And he's using one of the simplest animals that he can easily use to do that. So I've taken you down to a fruit fly. Now I'm going to take you down to something the size of a tenth of a hair, a protein complex. And the question here was, how do you see? It's like being a kid again. You keep asking questions. How do you see? Why do we see? How can something in your eye take light and turn it into thought and action? How does that happen? So they are using the simplest version of the eye that's possible. They're using this bacteria that's found everywhere in the US and every salty sea in the world, every salty sea. It's called E. halophila. And this thing loves to be in the sunshine, but it doesn't have eyes. How does it know when it's in the sunshine? So it has little flagella, it's swimming around, but it has a protein in its outer covering that's photosensitive. When it sees blue light, if it swam too deep and sees blue light, it gets a reaction and runs away. It noses away from the sun. So it has a protein molecule that's the basis of this thing. And inside this protein is a chromophore, a combination of a hexagonal ring of carbons with things. And when a light molecule hits it, this exact molecule has a reaction. And it was a little unexpected. When a light molecule hits it, it actually changes its shape, its conformation, and it actually, this tip takes a hydrogen atom from this molecule and puts it over here. It actually physically transports a hydrogen atom. It's taken light, one photon of light, and changed it into action. And what they were able to map on picoseconds, nanosecond scale is how the electrons are sloshing around in this molecule as it's exposed to light. So this is work by Professor Keith Moffat at University of Chicago and some of my friends, Ukita Schreier and others, that are doing on very, very fast timescales, trying to figure out how does a light molecule interact with a biological molecule to make something happen. So now we're at the molecular level. Oh, I forgot. So this is the scattering pattern that they see. The actual direct X-rays go through this tiny little hole, and then the X-rays that are scattering really far out tells you about the details very close in. So people in energy sciences are always using our beam. One of the big problems in the US is diesel engines. Okay, we got diesel fuel, we got biofuel, we're sticking them into these engines and we're wondering why we're not, these things aren't efficient. The X-rays go through everything. We can look at these diesel fuel injectors right as they're working in the engine. So these guys are imaging through an engine block. This is an injector, and watching how the fuel spray breaks up. And this is an actual fuel spray, a biodiesel fuel spray, how it injects into a compressing piston and how it's breaking up right before it ignites. And it's really interesting because all these different fuels, diesel or biodiesel, they all react differently. If we're really going to have a diesel truck society, we're going to have these injector nozzles that are able to adapt to different kind of fuels. Fuels with ethanol, fuels made from biosolids, fuels made from petroleum products. So they can look in and see how those work. Material science. The Dow people spend a lot of time at our place, and in 2013 they did a lot of research into this solar material. The powerhouse solar shingles are roof shingles that provide power to your house, and they started it was voted one of the best inventions in 2029, and they started a factory, and you can buy these now. You can make your roof a solar roof. And the exact material that converts light into energy took years of research to find out the right combination of materials to have high efficiency and long-lasting solar conversion ability. X-rays don't care if it's shooting through water, if it's shooting through steel. We have some people that are looking at molten material. This thing is heated up to white hot. It's 2,500 degrees Celsius. And they levitate a bead of this material on a little jet of air. They heat it to white hot, and we can look at it. We can look at all the different temperatures as it cools down and heats up, how this thing melts and transforms. So we can look at things in any kind of environment: vacuum, water, ultra hot, ultra cold. Lots of medical people come to use our facility. You may or may not know that viruses are they're sort of like small balloons. If I would sneeze on her and I had a cold, I would transmit a virus, it's called a virus capsid, to you in my sneeze. You know, the little drops of water that fly around when you sneeze. In those is something that sort of looks like this. It's a really thin skin of complicated interlinked proteins, and inside of this very thin skin is packed all the DNA of the virus. It's all folded up in there. And when this virus sees one of her cells, it will generate a point of attachment, sort of like a hypodermic needle. And that point of attachment will open up, and all that DNA will be funneled out, pushed out, like pushing a string through a hypodermic needle into her cell. And then her cell is hijacked. It makes millions of copies of it. It explodes. Those go and infect millions of more of her cells, and on and on. And the reason you have all the sneezing and the sniffling is because you're destroying all your cells, and your body's flushing them out, and your eyes are watering, and your nose is dripping, and it's all because you're destroying your own cells, making these virus capsids. And it's really important to know how these things are constructed. Every living thing in the world has multiple viruses that attack it. Not just people, not just goats or cows, corn, tomatoes, anything living has a virus who's evolved to attack that living thing. And drug companies are super interested in this because our immune system sees this. Our immune system sees this outer shell. And look at all these different varieties. And these outer shells change. They evolve, they mutate every year. That's why when we get one kind of cold, one year, we're not immune to it because the virus mutates and he has a different outside shell and he can't recognize it, and we get sick again. So virus companies want to know, atom by atom, molecule by molecule, what these things look like. So they can design drugs that go in and incapacitate it. That's the whole game. Can we do this fast enough? Can we find a new virus, figure out what it looks like, transmit the atomic coordinates of every molecule in there to a company who designs a drug that will incapacitate this thing before it spreads throughout society? So we do that, and here's how we do it. We make those little viruses into crystals, tiny little single crystals. Excuse me. We put them in the X-ray beam. We diffract, we scatter X-rays off of all the atoms in these crystals, and this is kind of like what the pattern looks like. We don't see the atoms. We see how they scatter the X-rays, and then we use computationally intensive ways to make models. We make thousands of models, and we simulate how these projected molecules would make a scattering pattern, and we fit, and we keep making new molecules, adjusting the molecule fit until we figure out what prototype molecule could make the exact same scattering pattern as the real one. And that's what we see is the structure of the thing. We don't see the structure of the actual virus. We make a model that behaves the same way in X-rays. And that's how we know what things look like, because things converge to an exact, to fit all these millions of points with the right intensities and the right spacing and the right distribution. There's a very specific combination of these millions of atoms, thousands of molecules, that will make that one diffraction pattern. And so this has turned into a big deal. We do this at the Advanced Photon Source and many places around the world. We do this daily, continuously, 24/7, every day of the year. We're looking at structures of all these different kind of viruses. We also use cool techniques like, as you imagine, X-rays will tend to burn through. If we couldn't hold a sample in the beam with our hand, that would be lethal. We can't hold it in there with on a big spoon. We like to hold it with nothing. Oops. So we use this technique, I'm going to try to run it again, called acoustic levitation. Okay. Here we go. Where you set up a sound wave, one frequency between two transmitters, and it sets up a standing wave field, just like standing water waves. Although this is standing acoustic waves, standing air waves. And these waves are strong enough that we can actually levitate and move things around in the X-ray beam in this. And computationally, we've gotten to the place that my desktop computer, we're going to try to simulate this acoustic wave, and I'm going to spray very fine mist of water in there. And we can now see maybe you can't see. Can you see the little dots of water being suspended in air? We can now model that in a computer system, very exactly. And so now we can do more and more complicated things, figuring out how each water molecule has gotten from a spray into this standing wave field. So a lot of my job is modeling and simulation before we actually do these things. Okay. There we go. Those of you interested in geology, the geologists use these X-ray facilities all the time. No. This is pretty interesting and pretty complicated. Let's say you want to figure out what's at the center of the Earth or at the center of Jupiter at super high pressures, super high temperatures. How do you do that? We do that experimentally. We take two diamonds, just like diamond rings, and we polish them down to sharp points, and we put those points together. And we have a little gasket of beryllium metal. It's a low atomic number metal. And you put a little force on a big area and transmit it down to a tiny pinpoint that multiplies that force. And the more mechanical force you put on the outside, it transmits down to a tiny little force. We can make forces, like I said, many, many gigapascals, many times the force at the center of the Earth. And so now we have a little sample of material, tiny little sample of material at pressures whatever we need, like I said, up to this pressure of the center of Jupiter, and we can heat these things with lasers. Diamonds don't care about laser rays coming through. X-rays don't care about lasers coming through. So this material thinks it's at the force at the center of the Jupiter and the pressure at the surface of the sun, and we can see what it's doing by passing X-rays through these materials and actually discovering what's going on in there. This is how we're figuring out deep earthquakes and the Earth mantle core boundaries, what the rocks are actually doing at those boundaries, how things are working. We're actually taking samples of real materials, taking them to the equivalent depth in the Earth, equivalent pressures, equivalent temperatures, and figuring out how they're changing. And a lot of these materials, surprisingly, they undergo a transformation where they actually crack, they snap into a new conformation, and they create very deep, that's what they think, creates very deep earthquakes. Different materials subducting into the center of the Earth, changing conformation, atoms packing closer together, causing deep earthquakes. What else have I got? Oh, environmental science. Environmental scientists love using X-rays. They had us study this little diatom. These little guys are all over the surface of all the oceans of the Earth, and they take carbon dioxide out of the air. They use it to make their little structures. We can pick X-rays of exactly the right energy to light up every individual element in the periodic table. And so we did that. We took this tiny little diatom and we lit up and we made a map of everything that this diatom needs to build its structure. Maybe sometime in the future, we found out that, for example, it makes little rings of iron. It's part of its structure. Maybe if we give them a little iron, we'll make more diatoms. It'll take more carbon dioxide out of the atmosphere. When they die, they go to the bottom of the ocean. Carbon monoxide is sequestered. It's taken out of the atmosphere. So these are nature's little cleanup animals. And by studying them, maybe we can figure out a way to remediate some of our current problems with greenhouse gases. Anyway, everyone in the world, now that I tell you, these are microscopes. These are super unique and super useful things. The Department of Energy, my boss, runs 5 of these in the United States. It takes a lot of people. It takes 400 people in this office building to keep this thing running day and night all around the clock. And the entire world realizes how useful these are. The Far East has 28 of them. Everything from synchrotron rings about the size of this round part here. Everything from those to the size of our machine. They're all kind. Like I said, the Far East has 28 of them. Europe has over 20 of them. We have a bunch of them. And the brand new ones, the forefront ones, the premier ones in the world, are actually new ones being built in Brazil and in Sweden. They're leading the world with their brand new facilities. So these are monumentally, mind-bogglingly useful devices. But there are 3 big ones in the world. This one in Japan called, I love how the Japanese name their things. It's Super Photon Ring 8, Spring 8. And the second big one is in Europe, in Grenoble, France, the European Synchrotron Radiation Facility. And the third big one in the world is right down the street from you at the Advanced Photon Source here at Argonne National Lab. It's a long walk, but we're right down the street. So I work at Argonne. I build these things. I used to use them to do the science. And then I used to run the facilities to help other people do the science. And now I build them so people can run them to use them to do science. So I build these things that solve some of the biggest problems in the world. But sometimes it's just too much to explain to people. I just say I drive a train. So that's it. That's what I've got. I'm happy to take any questions. It's a lot to take in, but we use every aspect of science, every aspect of engineering, every aspect of computational modeling and mathematics, and all the tech we can get to run this facility, to do science, big, difficult science that's supposed to make our world a better place. Okay, thanks.
Thank you. Any questions for Dr. Navrotski?
In regards to the 5 tricks you mentioned, since we can't see X-rays, what does the research process look like? Like when you're running the experiments, how do you know it's actually working?
It's a really good question. You're right, we can't see them. So we develop all these detectors. So if I would take the CCD camera out of my phone, and if I would put a material there are different materials that fluoresce. They light up in X-rays. If you had a geology class, you take an ultraviolet light, and you put it over certain rocks and they light up. Or if some of you know about black light posters, there are different materials that will take the energy of the X-rays and turn it into light. So we spread those materials on very fine CCD detectors, and the X-rays cause the material to light up, and the CCD detector sees the light from it. Sometimes we send the X-rays through different gases. When you send X-rays through things, the way it absorbs it is by throwing off electrons. If I would send an X-ray through your body, the most intense X-rays would shoot electrons off of all your atoms in your thing. And we can capture those electrons. And by knowing that there's so many electrons of a certain energy coming off, we can detect them. There's a lot of ways, but mostly we use CCD detectors that are specially made to see the X-rays, and electron detectors that sees the byproducts. We don't see the X-ray going through, we just see the result of the X-rays going through. So, yeah.
Any other questions?
So sometimes people ask me why we're not using these X-rays for things like mammography. We can get super high resolution with mammography. We really can't do things that big. We can only do things, I mean, like the knee of the worm. It's kind of the knee of the caterpillar is kind of the biggest thing we can see. All these X-rays are concentrated into a super small spot. And if we wanted to scan all of you, it would take us a long time to move you through the beam back and forth. So we don't do that. We don't do that. We do things that are on the millimeter down to subatomic scale. That's where we're best at. That's what we do best.
Any more questions? Well, I have a question. Could you comment on what we were speaking before about the level of physics and science, specifically mathematics, behind the research that you've done?
Oh, yeah. So as I showed you with the example of the virus, we scatter the X-rays off of the virus. We don't see the virus. We see the X-rays that have been deflected. And we take all that data, and it takes really a high level of computational complexity to take all that information and a model and match them together, to converge them together. Sometimes we do something called tomography. This is where you shine an X-ray through something, just like a CAT scan. If you have a scan of your knee or something, you want a three-dimensional image of it, you send the X-rays through, so it's absorbing through, and then you send it through again, and it's absorbing differently and differently and differently. You have to compute. Everything is computing of what the X-ray would do if the object looked like this, and you have to match that to reality. So it's super computationally intensive to get all this information. The data volumes are huge. We're generating terabytes per minute of data that have to be massaged and analyzed, and this is what takes the scientists most of their time, okay? They spend maybe weeks gathering the data, but they spend years analyzing the data. And they use the most sophisticated techniques you can imagine to take all this information and turn it into a model, a realistic model. We have a supercomputing center, and the number 5 supercomputer is right down the street from my building. We send those data volumes over to there. We send them down to Urbana-Champaign, which has another supercomputing center. We send them to the West Coast. And all this computation power is what it takes to take this experimental data and match it to reality. So there's a really, the people in the computing centers have a very high level of mathematical capability. Lots of, they turn the analytical equations into computational models that I can go and just put in stuff. I don't have to know the eigenequations or any of the complicated mathematics. I use the models that they create to solve my problems. So a lot of computation. Yeah.
Thank you. Any more questions? All right. Oh, yes.
You talk about X-rays being used to look at the fine details of things. Does that have an application like the world of computer manufacture, where you have to look at the individual circuits and such of a motherboard or whatever?
That's a surprisingly good question, because most of our computer chips are manufactured overseas. And we have a lot of people in the government that are afraid of what's in the computer circuit, since we don't control it. Are there hidden circuits in the actual computers we use? And so yes, we can use X-rays. We can map out each and every circuit. Sometimes these circuits are 60 nanometers wide. The lines that connect all these semiconductors, 60 nanometers. That's like 120 atoms wide. That's the width, the number of atoms that are transmitting the electric from one transistor to another. So we can map these out. But now that we're working at such a small scale, it takes a lot of time to do that. But yes, we can look. I forgot to say that these circuits are not just one layer of circuitry. They stack them up 16 deep now. And so if you're looking at this thing, even if you cut it apart, you've got 16 layers to go through, and they're all interconnected in very complicated ways. We're just to the point where we can image those things with tomography. We can make 3D models of what they look like, what they're supposed to look like. And you didn't hear it from me, but almost 10% of the circuits that people have examined have unknown circuitry in them. So people like the Defense Department they just get crazy when they hear stuff like that. They just go ballistic. They want to know exactly that every computer they're using is doing what it's supposed to do and not doing anything else. So yeah, it's a complicated process, but we can do it now. But right now it's at the heroic level. It takes a lot of effort to see all this detail at atomic scales. But we're going to get this automated. It's going to get easier as you guys start getting into the field and working on it, and we get more people to work on the complicated problems that go along with it. Yeah. Thanks. That's a good question.
All right, let's give a round of applause for
Thank you very
Dr.
much.
Navrotski.
Thank you all for coming out. I appreciate it very much. Thank you.
This concludes our STEM lecture series for the semester. If you need to sign in, there's a sign-in.